Every space colony that exists today depends on Earth for survival. Raw materials, food, medicine, technical expertise, and political authority all flow from the home planet like a lifeline. But what happens when that lifeline is severed? By the end of this story, you will understand how colonies forced to stand alone either collapse into chaos or transform into something far more resilient than anyone anticipated. What would trigger such a cutoff? How would colonists react when they realize no rescue is coming and no resupply ship will ever arrive? The answers reveal not just the fragility of our space ambitions, but the hidden strength that crisis can unlock. What do you think it really takes for humanity to survive without a safety net? Earth is not just a distant home world, it is the single point of failure for every colony. To understand why a cutoff would be so devastating, you have to look at the sheer volume of supplies and support that flows from the home planet. Imagine a colony as a newborn baby. It cannot feed itself, build its own shelter, or produce its own medicine. Everything comes from outside. On Earth, that outside is the global supply chain. In space, that outside is Earth itself. First, raw materials. Every ton of metal, every liter of water, every kilogram of soil used for agriculture has to be launched from Earth. The cost is astronomical. It takes enormous energy just to lift a single brick into orbit. Without that steady stream, colonies have no way to expand or even repair broken equipment. They are literally built from what was sent up, and that stockpile is finite. Then there are manufactured goods, computer chips, solar panels, life support systems, communication gear. These are not things you can easily fabricate in a hostile environment. A colony might have a basic workshop, but it cannot produce a new oxygen scrubber from scratch. It relies on shipments of precision parts. Food is another obvious lifeline. Even if a colony grows some of its own, the majority of calories and nutrients come in packaged form from Earth. Without resupply, the hydroponic gardens and algae vats cannot keep up with demand. Malnutrition would set in within months. Medical supplies are equally critical. Antibiotics, vaccines, surgical instruments, and advanced medications have a short shelf life. A colony cannot manufacture these from local resources. The first serious infection or injury after the cutoff could become a crisis. Personnel rotation is another hidden dependency. Crews rotate back to Earth to recover from bone density loss, radiation exposure, and psychological strain. Without that rotation, colonists face permanent physical decline. Their bodies were not designed for zero gravity or low gravity living. Financial backing is the invisible fuel. Colonies run on government grants and private investment. If Earth stops sending funds, the entire economic model collapses. No money to pay for maintenance, no incentive to continue research. Political legitimacy also matters. Colonies exist under treaties and agreements that grant them authority to govern themselves. If Earth cuts off communication and recognition, they become stateless outposts with no legal framework. Disputes over resources or leadership could spiral into chaos. So when we talk about a cutoff, we are not talking about a minor inconvenience. We are talking about the collapse of every system that keeps a colony alive. The foundation of colonial existence is this umbilical cord, and when it is severed, everything changes. The question is not whether hardship will come, but whether any colony has the capacity to survive the transition from dependency to independence. What would be the first thing to break, and what might be the first thing colonists discover they can do for themselves? Before the colony feels the strain, Earth itself must reach a breaking point. The triggers that sever the lifeline are not always dramatic, though some certainly are. They share one quality: they undermine Earth's ability or willingness to support distant outposts. Environmental pressures rank high among them. Climate shifts over decades can strain global food production, disrupt supply chains, and force nations to focus inward. When harvests become less reliable and coastlines change, the resources once earmarked for space colonies are redirected to urgent needs at home. The colony does not see this coming. It only notices when shipments become irregular, then stop entirely. Resource depletion follows a similar path. Key materials like rare earth elements or fossil fuels become harder to extract. The cost of launching anything into orbit rises astronomically. Eventually, Earth must choose between funding a hospital in a struggling city or sending a resupply rocket to a colony. The choice is almost always local. Prolonged conflict between nations can also fracture the support system. International cooperation is the glue that holds space programs together. When that cooperation breaks down over trade disputes or territorial disagreements, the supply chain splinters. Each nation prioritizes its own survival. The colony, built on shared investment, finds itself orphaned. Political isolationism is another quiet trigger. Governments change, public opinion shifts. A new administration may see space colonies as a luxury rather than a necessity. Funding dries up, treaties are abandoned. The colony is left to wonder if Earth remembers it exists. Lastly, a large-scale natural event or a global health crisis can overwhelm Earth's capacity entirely. Supply chains, hospitals, and governments become consumed with immediate survival. The colony, far away and silent, simply stops receiving replies. Each trigger leaves the same result: a colony alone, forced to confront its own survival. But the moment of realization does not come all at once. It arrives in stages, and how colonists respond in those first hours and days determines everything. The first sign is silence, not the silence of open space, but the silence of a channel that once hummed with data and voices. Colonists are used to a communication lag with Earth, a delay of several minutes each way. But that lag has always been predictable, a steady rhythm of messages traveling across millions of kilometers. Now the rhythm stops, replies do not come. The scheduled resupply window passes with no vessel in sight. At first, the crew assumes a technical glitch or a scheduling delay. They run diagnostics, check antenna arrays, and send repeated signals. Hours turn into days, the silence deepens. Then the psychological weight begins to settle. Every colonist understands the implication, even if no one says it aloud. Earth is no longer able or willing to help them. The realization is not a single dramatic moment. It creeps in like a slow leak in a pressure suit, barely noticeable until the air is gone. People gather in common areas, speaking in hushed voices. The usual routines of maintenance and research feel hollow. Some colonists stare at screens, refreshing dead links. Others retreat to their quarters. The colony itself, a carefully designed machine for survival, suddenly feels fragile. Life support systems still run. Lights still glow, but the knowledge that no spare parts, no fresh food, no medical evacuation will ever arrive transforms every familiar surface into a reminder of isolation. The supply chain halt is not abstract. It means the hydroponic bay cannot replenish its nutrient solution because the stock ran out. It means the workshop cannot replace a worn pump seal. It means the pharmacy cabinet holds exactly enough antibiotics for 2 minor infections, not a single outbreak. Colonists begin counting everything: meals, water rations, battery cycles, oxygen scrubber cartridges. The numbers are not reassuring. Leaders emerge, often the engineers and medical officers who are trained for emergencies. But this emergency has no protocol. No one planned for absolute cutoff. The first hours are marked by frantic assessment. Teams inventory every resource. They calibrate sensors to measure available power, water, and breathable air. They map out timelines, worst-case scenarios, and possible adaptations. The shock is still present, but it competes with an urgent drive to act. One colonist might suggest shutting down non-essential systems. Another argues for conserving food by reducing daily rations. Decisions must be made quickly, but without complete information. The colony becomes a pressure cooker of fear and determination. Some individuals freeze, unable to process the finality. Others move with a cold precision that surprises even themselves. The first moments after the cutoff are a test not just of technology, but of human resilience. And the choices made in these hours will echo through every day that follows. They do not panic for long. Within days, the colony shifts into a methodical, almost surgical mode of survival. Every colonist who can hold a scanner or carry a clipboard is pressed into service. The first task is not to build or repair, but to count. A complete inventory of everything the colony possesses becomes the single most important document anyone has ever created. They start with the obvious stored supplies: rows of freeze-dried meals, water tanks, oxygen canisters, medical kits, and spare parts. Each item is logged, weighed, and assigned an expiration date. The numbers are sobering. Most colonies stock only enough for a planned resupply cycle, not for indefinite isolation, but the real treasure lies hidden in the environment around them. Water ice is the first critical resource. Many colonies are built near known deposits of water ice, whether on the Moon, Mars, or an asteroid. The colony's survey data from previous missions already maps these reserves. Colonists pull up geological scans and radar readings. They calculate how much ice is accessible, how deep it lies, and how much energy it takes to mine and melt it. Every kilogram of water is potential drinking water, breathable oxygen, and rocket fuel. The ice becomes a lifeline measured in liters and years. Next comes regolith, the loose soil and rock covering the surface. It looks like gray dust, but it is packed with metals, silicon, and oxygen. Colonists know that if they can process regolith, they can extract aluminum, iron, titanium, and even create building materials. The colony's workshop might already have a small 3D printer designed to use regolith as feedstock. They test samples, run chemical assays, and determine which areas yield the richest deposits. Regolith becomes their quarry. Atmospheric gases, if they exist, are another vital find. On Mars, the thin carbon dioxide atmosphere can be concentrated and split into oxygen and carbon monoxide. The colony's life support systems may already have a small oxygen generator. Engineers dust off the blueprints and evaluate how to scale it up. Even a modest output buys time. On the Moon or an asteroid, there is no atmosphere, so they must rely on water electrolysis or chemical extraction from regolith. Energy reserves are the engine of survival. Solar panels, nuclear batteries, and fuel cells are inventoried down to the last watt-hour. Colonists calculate daily power consumption and compare it to peak generation. They identify non-essential systems to shut down. They examine backup batteries and determine how long they can sustain critical life support if primary power fails. Every decision about energy use becomes a trade-off between comfort and longevity. Manufacturing equipment is the workshop's soul. Lathes, drills, welding torches, and 3D printers are listed along with their spare parts and tooling. Engineers test each machine, calibrate sensors, and stockpile lubricants. They discover that even a simple lathe can be used to produce replacement bolts, pipe fittings, and structural brackets. The colony's survival hinges not just on raw materials but on the ability to transform them. Finally, the most valuable inventory is human skills. The colony's roster includes engineers, doctors, botanists, geologists, and technicians. But also cooks, mechanics, artists, and teachers. Everyone fills out a skills survey. A former carpenter might know how to build a strong frame. A hobby chemist might understand how to extract minerals. A retired military officer might have logistics training. These hidden talents, never listed in official mission profiles, become the colony's greatest asset. The entire inventory process is guided by pre-existing data from in situ resource utilization studies, or ISRU. These studies, conducted before the colony was built, mapped exactly what local resources were available and how to use them. Colonists pull up those old reports and cross-reference them with current conditions. The data is not a plan, but it is a map, and on that map they see the faint outlines of a path forward. They learn that survival is not about how much they brought, but about how much they can find, make, and grow from the world around them. The inventory does not guarantee success, but it reveals exactly how much time they have to learn a new way of living. The inventory reveals a harsh truth. Time is not measured in days, but in the steady pulse of life support systems. Oxygen circulators hum, water recyclers drip, temperature regulators click, and radiation monitors blink. These machines are the colony's lungs and kidneys and skin and bones all at once. Without Earth, there are no replacement parts. There are only clever adaptations, careful rationing, and relentless maintenance. The margin for error has vanished. Oxygen is the first and most urgent priority. Colonists run a full audit of every oxygen generator, every scrubber cartridge, and every backup tank. They discover that the primary oxygen generation system, which uses electrolysis to split water into breathable air, is the most efficient but also the most delicate. It requires precise voltage, clean water, and rare catalyst materials that cannot be replaced. Engineers immediately shift to a lower power setting to extend the catalyst's lifespan. They also test the backup chemical oxygen generators, the ones meant for emergencies, and confirm they still function, but those are finite. Each cartridge produces a fixed amount of oxygen and then becomes useless. The colony decides to reserve them for true emergencies only. Water is equally critical. Every drop of moisture is captured, filtered, and reused. The colony's water recycling system is a marvel of engineering, but it depends on filters and membranes that degrade over time. Colonists estimate how many cycles each filter can survive before it must be replaced. They search storage rooms for spare cartridges and find only a few. The answer is not to use less water because the body needs hydration, but to reduce losses. They repair every tiny leak in pipes and connectors. They check seals on storage tanks. They even collect condensation from the walls and windows. Nothing is wasted. Temperature control systems work around the clock. Outside the colony, temperatures swing from deadly cold to blistering heat depending on the world and its orbit. Inside, every degree is carefully regulated. Radiators and heaters are checked for blockages. Insulation is inspected for damage. Engineers discover that a small vent had been slightly open, wasting precious heat. They seal it immediately. The colony's temperature stability depends on a delicate balance between internal heat from electronics and humans and external extremes. Any imbalance could freeze crops, damage equipment, or stress life support. Colonists set strict temperature limits, slightly wider than comfortable, to reduce strain on the systems. Radiation shielding is the least visible threat. On Earth, the atmosphere and magnetic field protect everyone. In space, solar flares and cosmic rays are constant. The colony's outer walls contain layers of water, polyethylene, or regolith to absorb radiation. But these layers can degrade or shift over time. Colonists run radiation detector surveys across every module. They map hotspots where shielding is thinnest. In some areas, they stack extra water containers or bags of regolith to increase protection. Sleeping quarters are rearranged so colonists rest in the safest zones. The colony cannot stop all radiation, but it can reduce exposure to levels the body can tolerate over years rather than hours. Rationing is not just about food. It applies to every life support resource. Colonists calculate daily allowances for water, oxygen, and power. They post schedules and limits. Showers become sponge baths. Laundry cycles are reduced, lights dim in corridors, kitchen appliances are used in shifts. Every colonist receives a clear allocation and must make it last. The colony becomes a closed loop, and every loop must balance. Immediate repairs are the third pillar beyond redundancy and rationing. Colonists spend the first weeks patching, reinforcing, and stabilizing. A cracked pipe in the water recycling unit gets soldered. A failing fan motor in the air circulation system is replaced with a salvaged part from a non-essential experiment. A worn seal on a hatch is coated with a homemade epoxy from regolith dust and resin. These are not permanent fixes. They are temporary bridges until a better solution can be engineered. The atmosphere inside the colony shifts. People speak in quieter voices. They move with deliberate care. The machines hum on, but now every sound is monitored. Colonists learn to hear the subtle change in a pump's pitch that signals wear. They learn to smell the faint chemical hint of a filter nearing exhaustion. The colony becomes a living artifact of human ingenuity, stretched thin but holding. Life support is the foundation. Without it, no plan for food, manufacturing, or exploration matters. The colony must keep its air breathable, its water clean, its temperature stable, and its people shielded. Every other priority follows from this single truth. The colony does not just live inside its systems. It is those systems, and every day that the machines run, the colony earns another day to learn, adapt, and survive. The colony's food supply is measured not in months but in meals. Every package of freeze-dried vegetables, every pouch of protein, every sealed bag of rice represents a finite number of days. When the last crate is opened, the colony will face a stark choice: grow food locally or go hungry. The transition from Earth-supplied stores to self-sustaining agriculture is not a simple shift. It is a complete transformation of how the colony uses its space, energy, and human labor. The first step is to expand beyond the small experimental garden that most colonies maintain. Those gardens are a proof of concept, not a lifeline. Now they must become a full-scale production system. Hydroponics is the most straightforward method. Plants grow in nutrient-rich water instead of soil. The colony already has a modest hydroponic setup, perhaps a few trays of leafy greens and herbs, but scaling up requires more room. Every unused corridor, every storage closet, every corner of the habitat module becomes a potential growing surface. Colonists convert common areas into vertical farms, stacking trays of lettuce, kale, and spinach under LED lights. The water is recycled from the life support system. The nutrients, however, are a problem. Hydroponic solutions require precise mixtures of nitrogen, phosphorus, potassium, and trace minerals. Without earth, these must be extracted from local resources or reclaimed from waste. Colonists begin composting organic scraps and processing human waste through a closed-loop system. They grind up leftover plant material, dry it, and ash it to recover minerals. They test the ash composition and adjust the nutrient mix. It is crude but functional. Every cycle reduces the colony's dependence on imported chemicals. Aeroponics offers an even more efficient alternative. Roots hang in the air and are misted with nutrient solution. This uses less water and less space than hydroponics. Colonists who join the mission with a background in agriculture quickly become the most important members of the crew. They design misting nozzles from salvaged medical syringes and pressure regulators from old plumbing parts. The nutrient mist is recycled and filtered. Aeroponic systems can grow tomatoes, peppers, and even small root vegetables like radishes in a fraction of the area required by traditional farming. But these systems demand constant attention. A failed pump or a clogged nozzle can kill an entire crop in hours. algae bioreactors are the workhorses of the new food system. Algae grows rapidly in simple tanks filled with water, light, and carbon dioxide. The colony's air circulation system already captures CO2 from human respiration. Diverting some of that CO2 into algae tanks is a natural fit. The algae are not appetizing on their own, but they can be processed into a protein-rich paste. Colonists mix it into bread, soups, and supplements. The bioreactors also produce oxygen, which helps stabilize the life support system. A single square meter of algae can yield more protein than a square meter of soybeans. But the energy cost is high. The tanks need consistent lighting and temperature control. The colony's power budget must stretch further. Lab-grown protein is the final piece of the puzzle. Cells from a small sample of animal tissue can be cultivated in a nutrient broth to produce muscle fibers. The process requires sterile conditions, precise temperature, and a continuous supply of amino acids and growth factors. Those growth factors are complex molecules that the colony cannot yet synthesize. They must be extracted from algae or from the colony's own waste streams. It is a slow, expensive process, but even a small bioreactor can produce enough protein to supplement the diet. Colonists learn to integrate every scrap of biological material into the food chain. Seed banks become a sacred trust. The colony likely brought a diverse collection of seeds for research and emergency food. These are not just seeds, they are genetic libraries. Each packet holds the potential for generations of crops. Colonists catalog the seeds by germination rate, growth time, and nutritional yield. They prioritize fast-growing varieties like beans, peas, and leafy greens. They also preserve heirloom varieties for long-term genetic diversity. A single failed crop season could be catastrophic, so they split the seeds into multiple locations within the colony. One cache is kept in a refrigerated storage unit. Another is planted in a rotating schedule to maintain a living seed bank. Microbial cultures are equally vital. The colony's soil substitutes, whether hydroponic solutions or aeroponic mists, depend on beneficial bacteria and fungi to break down nutrients and protect against pathogens. Colonists maintain a culture collection of these microbes. They freeze dry samples and store them in small vials. They also cultivate active cultures in continuous fermentation vessels. A lost culture could mean a cascade of crop failures, so they treat the microbes with the same care as the seeds. Energy is the invisible barrier. Growing food at scale requires enormous amounts of artificial light, temperature control, and pumping power. The colony must allocate a significant fraction of its energy budget to agriculture. This means shutting down non-essential research, reducing lighting in living quarters, and running pumps and fans only during specific hours. Every kilowatt-hour diverted to a grow light is a kilowatt-hour not available for life support or manufacturing. Colonists optimize by growing crops that are most efficient per unit of energy. Algae and microgreens yield the most calories per watt. Potatoes and grains are less efficient but more filling. They create a rotating menu based on energy cost and nutritional need. Space is the other constraint. A colony designed for 100 people might have a few dozen square meters of growing area. To feed 100 people, they need at least 10 times that. Colonists convert recreation rooms, unused laboratories, and even the medical bay into production zones. They remove furniture and install shelves of trays and tanks. The habitat becomes a living machine. A person stepping through a corridor might pass walls of green leaves, the hum of pumps, and the faint scent of damp soil substitutes. The entire colony begins to smell like a greenhouse. Food self-sufficiency is the first major milestone because it proves that the colony can sustain itself from local resources. It is not just about calories, it is about independence. Every crop harvested reduces the colony's link to Earth. Every successful harvest builds confidence. The day the first full meal made entirely from colony-grown ingredients is served, the mood shifts. It is a small meal, perhaps a bowl of algae soup with a side of hydroponic lettuce and a flatbread made from lab-grown protein. But it is a meal that required nothing from Earth. The colony has taken its first real step toward permanence. The path ahead remains long and uncertain, but the seed of survival has taken root. Energy is the invisible currency of survival. The colony can mine water and grow food, but without power, every machine falls silent. The air stops circulating, the water stops flowing, and the lights that nurture the crops fade to black. The colony's energy infrastructure was designed for support from Earth, not for indefinite isolation. Now that support is gone, and every watt must stretch further than ever before. Solar panels are the most visible source. Arrays of photovoltaic cells stretch across the surface, converting sunlight into electricity. On a moon or planet with a thin atmosphere, those panels work well during the day. But night brings a brutal drop in generation. On the moon, a single night lasts 14 Earth days. The colony must store enough energy in batteries to survive that long darkness. And those batteries degrade. Each charge cycle wears them down a little more. Without a factory to produce new lithium-ion cells, the colony must carefully manage charge levels, never draining them fully, never overcharging them. Engineers learn to extend battery life by cycling them shallowly, but eventually the batteries will fail. The search for alternatives never stops. Nuclear fission reactors offer a steady, round-the-clock supply. Many large colonies include a small reactor, often a compact design that uses enriched uranium or plutonium. These reactors produce heat, which is turned into electricity through turbines. They do not depend on sunlight. They can run for years on a single fuel load, but they are complex machines. They require coolant pumps, control rods, and shielding. Each component has a limited lifespan. A single failed seal or pump can shut down the reactor permanently. The colony's engineers treat the nuclear reactor like a sacred artifact. They monitor every temperature reading, every vibration signature, every chemical trace in the coolant. They know that if the reactor stops, their margin for survival shrinks drastically. They also face a difficult choice: run the reactor at full power to support expansion, or throttle it back to conserve fuel and extend its operational life. The decision ripples through every other system. On some planetary bodies, geothermal energy might be an option. On a world with internal heat, such as a moon with tidal heating or a planet with volcanic activity, drilling deep enough can tap into that warmth. The heat can be used directly for heating habitats or to drive turbines for electricity. But drilling requires heavy equipment, precise engineering, and energy itself. It is a long shot. The colony would need to confirm the geothermal gradient, choose a suitable site, and construct a borehole without the heavy drilling rigs that Earth provides. It is a project that could take years of manual labor and resource allocation. Still, if successful, geothermal would provide a stable, low-maintenance power source that does not rely on sunlight or finite nuclear fuel. The colony might send out survey teams to scan for heat anomalies using infrared cameras and seismic sensors. Every promising reading becomes a beacon of hope. Maintaining the entire power grid is a daily struggle. Cables corrode, connectors loosen, and transformers wear out. On Earth, a replacement part is a phone call away. Here, every broken fuse must be repaired by hand. Engineers learn to strip old electronics for reusable components. They solder wires, recoat insulation, and rebuild circuit boards from scavenged parts. They create a parts library cataloging every resistor, capacitor, and relay in the colony. The grid itself is a patchwork of high-voltage lines and local distribution networks. Power must be balanced across modules. A sudden spike from a pump starting could trip a breaker and plunge a section into darkness. operators schedule high-draw activities like welding or water pumping during off-peak hours. They install manual load-shedding switches so they can cut power to non-critical zones first, preserving life support and agriculture. Energy rationing becomes part of daily life. Each colonist receives a personal power allowance measured in watt-hours. They use it for personal devices, lighting in their quarters, and small appliances. Exceeding the allowance triggers a warning. Repeated overuse forces a temporary shutdown of their module. It is a system that fosters discipline and resentment in equal measure. Common areas are dimly lit. Corridors use only enough light to see clearly. The colony's computers operate on a priority schedule, with research tasks given lower priority than life support monitoring. The colony's leadership holds regular town hall meetings to explain the current energy status. They show charts of generation versus consumption. They announce when a new solar panel is installed or when a reactor component is repaired. Every small gain in efficiency is celebrated. The search for new sources never stops. Engineers experiment with thermoelectric generators that convert waste heat from the reactor into a few extra watts. They test small wind turbines on worlds with thin atmospheres, finding that even a light breeze can add a trickle of power. They consider building a solar updraft tower, a tall chimney that heats air at the base and drives a turbine. The construction is massive, but the materials can be sourced from regolith. They even look into nuclear fusion, but that requires technology far beyond what any colony possesses. It remains a distant dream. The colony learns to treat energy as the most precious resource, more valuable than water or food, because without it, nothing else can be made or moved. And they understand that the day the lights go out is the day the colony dies, so they work tirelessly to keep the grid humming, knowing that every watt earned is another breath of life. Power flows through wires and circuits, but it takes more than electricity to keep a colony alive. It takes things, physical objects, bolts and gears and pumps and pipes. Every component of every system was manufactured somewhere, and without Earth, that somewhere must become the colony itself. The moment a critical part breaks, and it will break, the colony faces a choice: fix it, fabricate a replacement, or watch a system fail. There is no fourth option. Three-dimensional printing becomes the colony's most versatile tool. These machines can build objects layer by layer from digital designs, and they work with a surprising range of materials. The colony's workshops already contain 1 or 2 3D printers, originally used for prototyping and spare parts. Now they become the heart of the industrial base. Engineers learn to print using regolith mixed with a binding agent, turning lunar or Martian dust into solid bricks, brackets, and structural panels. They experiment with different compositions, adjusting the ratio of regolith to binder until the printed parts are strong enough to bear load. A cracked wall panel can be scanned, measured, and replaced within hours. A broken handle on a hatch can be printed overnight. The ability to turn local dirt into usable objects changes everything. Metalworking follows the same principle of local resourcefulness. The colony mines metal from regolith, using processes like molten salt electrolysis or solid oxide electrolysis to extract iron, aluminum, and titanium. It is slow and energy-intensive. Each kilogram of metal requires hours of furnace time and significant power, but it is possible. Colonists build small foundries from salvaged refractory bricks and heating elements. They melt scrap metal from failed experiments, old tools, and damaged equipment. They cast new parts using sand molds made from fine regolith. A broken gear in a water pump becomes a casting project. A worn drill bit is reforged into a smaller tool. Nothing is thrown away. Every scrap of metal is a resource waiting to be reborn. Electronics repair is the most delicate challenge. Circuit boards, sensors, and microcontrollers are the nervous system of the colony. They cannot be smelted from ore or printed from dust. They must be harvested, repaired, and reused with extreme care. Colonists with steady hands and a background in electronics become the colony surgeons. They desolder damaged components, test resistors and capacitors, and replace them with parts scavenged from non-essential equipment. A failed oxygen sensor might be revived by swapping a chip from an old experiment. A dead control board in the water recycling system might be rebuilt using components from a broken computer terminal. Every piece of electronic waste is catalogued and stored. The colony becomes a museum of used parts, each one holding potential for a future repair. The soldering iron becomes as important as the welding torch. Recycling is the philosophy that binds all these efforts together. The colony cannot afford waste. Every broken object is not trash but raw material. Plastic containers are melted down and reformed into new shapes. Old clothing is shredded and pressed into insulation boards. Biological waste is composted or processed for nutrients. Even the dust that accumulates in air filters is analyzed for trace metals. Colonists establish a sorting system with bins for different material types. They train everyone to think in loops. A cracked mug does not go into a trash bin. It goes into the ceramic recycling bin, where it will eventually become a new component in a thermal shield. A torn glove is not discarded. It is disassembled, the fabric reused for patches, the metal cuff reclaimed. The colony operates on a principle that nothing is ever truly consumed. It is only transformed. The industrial base must grow beyond its initial capacity. Colonists build new workshops from salvaged shipping containers and prefabricated panels. They install a second 3D printer, this one designed for larger objects like replacement furniture and structural beams. They construct a small rolling mill that can flatten reclaimed metal into sheets. They build a wire drawing station that pulls thin copper wire for electrical repairs. Every addition multiplies the colony's ability to respond to future failures. The workshop becomes a noisy, crowded space filled with the smell of hot metal and the whine of motors. It is the colony's engine room, the place where raw materials become the parts that keep everything running. Specialization emerges naturally. Some colonists develop skill with the 3D printers, learning to optimize print settings for strength and speed. Others become masters of the foundry, able to identify the right temperature for each alloy by the color of the molten metal. A few become the colony's electronic wizards, capable of diagnosing a dead circuit by sound and smell. These specialists train apprentices, passing on their knowledge so that the skills survive even if they do not. The colony becomes a school of hands-on engineering, where every failure is a lesson and every repair is a victory. The psychological effect of this capability is profound. Each time a broken part is replaced by a 3D printed copy, or a salvaged component brings a dead system back to life, the colony gains confidence. The fear of an unrecoverable breakdown begins to fade. Colonists start to believe that they can fix almost anything given enough time and ingenuity. They learn the rhythm of maintenance, the cycle of wear and repair that defines their new existence. The colony becomes a living workshop, always building, always mending, always preparing for the next failure. And in that constant work, they find a purpose that fills the silence left by Earth. They are no longer waiting for rescue. They are building their own survival, one repaired part at a time. Health becomes the most fragile thread in a colony's survival. The body is a system of systems, and unlike the machines in the workshop, it cannot be rebooted or rebuilt from a digital file. When the last supply rocket from Earth fails to arrive, the medical cabinets hold exactly what they hold. There will be no more shipments of antibiotics, no sterile surgical gloves, no fresh vials of insulin or painkillers. The colony must learn to practice medicine with a finite pharmacy and a shrinking margin for error. The first step is a careful audit of every pill, every vial, every bandage, and every piece of equipment. Colonists log the expiration dates, the dosages, and the storage conditions. They discover that many medications degrade faster than expected in low gravity or fluctuating temperatures. Refrigeration units become the most guarded spaces in the colony, sealed and monitored around the clock. The stockpile of antibiotics, in particular, is precious. A single infection could consume what remains of a broad-spectrum course. Colonists learn to use them only when absolutely necessary, relying on antiseptic practices and early symptom tracking to avoid the need for heavy drugs. Local production of pharmaceuticals becomes a hidden priority. The colony can grow algae and ferment cultures, and from those they can extract simple compounds. Yeast can be genetically modified to produce basic insulin or small protein drugs. The colony might have brought a few vials of engineered yeast strains for research. These are now the seed of a pharmaceutical industry. Technicians learn to purify the output through simple chromatography columns built from plastic tubing and glass beads. The yield is tiny, a few doses per month, but each dose represents a life saved. They also learn to synthesize basic pain relievers and antiseptics from chemical precursors extracted from regolith. A burned wound might be treated with a paste made from local minerals and a reused dressing. Every treatment is improvised, tested, and documented. The role of the medical officer expands beyond training. Most colonies launch with 1 or 2 doctors skilled in emergency and preventive care. Now those doctors must become multidisciplinary surgeons, pharmacists, epidemiologists, and mental health counselors. They cannot do it alone. They train volunteers in basic wound cleaning, in monitoring vital signs, in recognizing the early signs of infection or organ failure. Every colonist attends classes in first aid and sanitation. The colony adopts a strict hygiene protocol. Hands are washed with reclaimed water. Surfaces are wiped down with a solution of vinegar and hydrogen peroxide produced from local electrolysis. The goal is not to eliminate all pathogens, because that is impossible, but to slow their spread and give the immune system time to work. Artificial intelligence diagnostic systems offer a form of backup intelligence. The colony's medical computer contains vast databases of symptoms, treatment protocols, and drug interactions. It can scan a patient using an array of sensors, analyze blood samples, and suggest a likely diagnosis. The AI is not perfect. It cannot perform surgery or hold a steady hand, but it can guide a colonist through a procedure, step by step, if the connection to the instruments remains intact. Colonists learn to trust the machine's recommendations while also checking for errors. They run simulations on historical cases to train themselves. The AI becomes a silent partner in every medical decision, a repository of knowledge that no single human could hold. But the greatest threat is the unknown. Every new environment carries the possibility of novel pathogens, unexpected reactions to local dust or solar radiation, or injuries that the medical database never anticipated. A colonist might develop a persistent cough from inhaling fine regolith particles that accumulate in the lungs. Another might suffer a burn from an unexpected chemical reaction during a mining operation. The colony has no allergen tests for local materials, no vaccine for an organism that has never been encountered. The risk forces a new approach to every task. Assume contamination, assume sensitivity, proceed with caution. Minor symptoms are tracked and reported immediately. A single case of unusual fatigue might trigger a full environmental scan to find the cause. The psychological burden of all this is heavy and quiet. Every colonist knows that a serious ailment, a complex fracture, a deep infection, a cancer that was once treatable with Earth's advanced therapies, may now be a sentence of chronic pain or a slow decline. They carry this knowledge with them into every duty shift, every meal, every conversation. It changes how they take risks. A simple slip on a ladder becomes a potentially catastrophic event. A small cut that does not heal becomes a source of deep anxiety. The colony develops a culture of mutual care. People check on each other, not for symptoms alone, but for the emotional weight that silence can carry. They create small rituals, a shared cup of rehydrated tea, a moment of quiet before sleep, a simple question about how the day went. These human touches become the strongest medicine of all. The colony learns to live with a different relationship to health. It is not about curing everything. It is about managing, adapting, and accepting limits. The doctors and the AI together can handle many routine problems, but every colonist understands that they are on their own in a way that no human has ever been. And that understanding, once fully accepted, becomes a source of resilience. They stop measuring time by what Earth could once provide. They start measuring it by how long they can keep each other whole. Communication with Earth faded slowly, then all at once. At first, the delay stretched from minutes to hours, then to days, until finally, no signal came at all. The colony's antenna dishes remained pointed toward the home planet, locked onto coordinates that no longer returned a voice. Operators ran diagnostic after diagnostic, recalibrated frequency bands, even climbed the exterior to check for physical damage. The hardware worked perfectly. The silence came from the other end. The loss of real-time conversation was more than an emotional blow. It was the severing of the colony's connection to the sum of human knowledge. For decades, every colony had relied on Earth's vast digital libraries, its research databases, its engineering archives, and its medical references. A colonist troubleshooting a broken water pump could query a database containing every manual, every repair log, every design specification ever created. A doctor facing a rare symptom could search through millions of case studies. Now that access was gone, what remained was whatever data had been stored locally before the cutoff. And that data was incomplete. The colony had cached portions of Earth's knowledge base, but caching is selective. A research station might have extensive databases on geology and life support, but sparse information on advanced manufacturing or crop genetics. The gaps were not random. They reflected the priorities of the original mission, not the needs of an independent settlement. Colonists began to discover these gaps in the worst possible way. An engineer trying to fabricate a replacement valve would find detailed diagrams for a different model. A botanist researching a new fertilizer formula would hit a dead end in the references. The colony's local servers held terabytes of information, but terabytes are a drop in the ocean of Earth's collective knowledge, and the data that did exist began to degrade. Storage drives have finite lifespans. Radiation, temperature fluctuations, and simple wear can corrupt files over time. A perfectly readable manual might develop a few corrupted pages. A medical algorithm might lose its calibration data. The colony's information environment was not static. It was slowly eroding, like a library where books fade and crumble with each passing year. Colonists responded by becoming digital archaeologists. They created backup copies of every critical file, storing them on multiple drives in different locations. They printed out paper copies of the most essential instructions, life support procedures, medical protocols, crop planting guides. A printed page does not depend on electricity or magnetic storage. It survives. The colony's printers ran continuously, churning out binders and manuals. Each printed document became a small fortress against information loss. But the problem ran deeper than corrupted files. Without access to Earth's ongoing research, the colony could not update its knowledge base. A breakthrough in water recycling efficiency, a new treatment for radiation exposure, a better alloy for structural supports. All of that remained unknown. The colony was frozen in time, operating on the science of the day it was launched. Its technology would not improve. It could only maintain what it had and learn from trial and error. That trial and error was slow and costly. A mistaken experiment might waste precious resources. A wrong assumption about a material property could cause a structural failure. The colony learned to document everything obsessively. Every repair, every failure, every adaptation was recorded in detailed logs. These logs became a new kind of knowledge base, one built from local experience rather than Earth's archives. But this local knowledge was scattered and incomplete, and the isolation was not just from Earth. As the drift continued, colonies on different worlds lost contact with each other. The Moon could no longer reach Mars. Mars could not hear the asteroid outposts. Each colony became a separate node in a fading network. The technology to maintain interplanetary communication still existed, but the expertise to operate it faded. Antennas were repurposed, frequencies were reassigned. The faint signals that once linked the colonies became weaker, then silent. Each colony was left with only its own population, its own stored data, and its own version of the truth. Over years, this fragmentation would lead to divergent knowledge bases. One colony might master a particular method of metal extraction, while another perfected a strain of algae that produced 5 times more protein. Without communication, these advances remained isolated. The colonies were evolving in different directions, each solving the same problems in its own way. Some solutions would be brilliant, others would be dead ends, and the colonists would never know which was which. The loss of connection was not just technical. It was cultural. Earth shared stories, its news, its music, its debates, all of that vanished. The colony's reference libraries contained snapshots of human culture, but snapshots grow stale. New books, new films, new scientific papers, new art never arrived. The colony's cultural evolution became entirely internal. Songs were written by colonists, stories were told by colonists, and those stories reflected only the experiences of a small group in a harsh environment. The human narrative narrowed. The colonists were no longer participants in a global conversation. They were curators of a museum of human history, with no new exhibits arriving. And yet, there was something powerful in that silence. The colony had to become its own source of knowledge, its own teacher, its own historian. Every experiment that succeeded was added to the local archive. Every mistake was recorded as a lesson. The database was no longer a mirror of Earth's past. It was a diary of the colony's present, and over time, that diary would become the only record of a new branch of human experience. The question was not whether the knowledge base would degrade. It already was. The question was whether the colony could build something new from the fragments that remained. Silence filled the space between people as much as between stars. The colony's physical walls pressed close, but the real confinement was social. Every face became familiar, every voice predictable, every habit a source of either comfort or irritation. The small group of colonists, once strangers united by a shared mission, now faced the challenge of living together indefinitely with no escape, no vacation, no rotation back to Earth. The dynamics that had worked for a 2-year mission began to fray under the weight of permanence. Cooperation remained the dominant force. Survival demanded it. A colonist who hoarded extra food or refused a shared task would endanger everyone. The community quickly developed an unspoken code: pitch in or let the colony slip toward failure. But cooperation did not mean harmony. Disagreements over resource allocation, work schedules, and personal habits surfaced daily. A minor complaint about a messy workspace could spiral into a lasting rift if left unaddressed. The colony needed a way to resolve conflicts without the safety valve of distance or the intervention of outside authority, so new norms emerged organically. Colonists began holding regular community meetings, not just to discuss work but to voice frustrations in a structured, neutral setting. A rotating facilitator, someone not involved in the dispute, would guide the conversation. The goal was not to assign blame but to find a solution that kept the group functional. Over time, these meetings became a ritual, a predictable space where tension could be released before it festered. Trust grew not from friendship alone but from the knowledge that every colonist had a forum to be heard. Mental health became a quiet priority. The strain of confinement, the absence of earth, the relentless pressure to perform, all of it accumulated like sediment. Some colonists withdrew, speaking less, eating less, retreating to their quarters. Others became restless, pacing corridors, seeking any distraction. The colony's medical officer recognized the signs of depression and anxiety, but the treatment options were limited. There were no therapists, no medications beyond a basic supply. The solution had to be social. The community created informal support networks. Colonists paired up as check-in buddies, each responsible for noticing if the other seemed off. They introduced a simple rule: no one eats alone. Mealtimes became a non-negotiable gathering, a time to share not just food but the day's small events. The act of breaking bread together, even if that bread was a rehydrated biscuit, reinforced the sense of belonging. Entertainment was scarce but essential. The colony's digital library held thousands of books, films, and music files, but they were finite. People began rewatching the same movies, rereading the same novels. The novelty faded, so the colonists invented new forms of play. They held storytelling nights where each person contributed a sentence to a collective tale. They created a game using salvaged electronic components and a digital scoreboard. They organized zero-gravity sports in a large storage module, adapting Earth games to the low-gravity environment. Laughter echoed in corridors that had been silent for weeks. These small acts of creativity were not trivial. They were the colony's way of reminding itself that life was more than survival. Privacy became a rare and cherished commodity. In a habitat where every wall had a window and every room served multiple functions, true solitude was nearly impossible. Colonists learned to signal their need for space. A closed curtain on a bunk meant do not disturb. A pair of headphones worn even without music meant I am not available. The community respected these signals. They also created designated quiet zones, small nooks where no conversation was allowed. These spaces were not luxurious. They were just a few square meters with a chair and a dim light. But they offered a psychological refuge, a place where a person could sit alone with their thoughts without being watched or expected to perform. The emergence of new cultural norms was gradual but unmistakable. The colony began to develop its own traditions, a weekly night where everyone shared a meal they had grown themselves. A ceremony for marking the passage of time, such as a small gathering when a crop was harvested. A ritual of gratitude at the end of each shift, where colonists thanked someone who had helped them that day. These practices had no precedent on Earth. They were invented, tested, and refined by the community. They gave the colony a sense of identity separate from its origin. The children who might be born in that environment would grow up knowing only these customs. They would not miss Earth because they had never known it. And the adults, the ones who still remembered blue skies and open horizons, had to decide whether to cling to those memories or embrace the new world they were building. Some chose to preserve Earth traditions, celebrating familiar holidays with adaptations. Others embraced change, letting go of old rituals that no longer fit. The tension between nostalgia and innovation became another layer of social negotiation. But the colony had one advantage that Earth societies rarely possessed. Everyone was invested in the outcome. There was no escape, no exit, no alternative. Every colonist knew that their survival depended on the group's ability to function. That knowledge forged a bond stronger than any contract. The social fabric was stretched and tested, but it held, and in the stretching it became something new. The colony was not just a collection of individuals anymore. It was a community with its own rhythms, its own stories, its own way of being human in a place where no human had ever been intended to stay. The silence of space pressed in from all sides, but inside, a new kind of noise was being born, the sound of people learning to live together forever. The colony had no constitution, no elected officials, no written laws. All of that had belonged to Earth. Now, in the silence left by the home planet, the colonists had to build a system of governance from scratch, one that could handle decisions where the wrong choice meant death. The first step was not dramatic, it was practical. A small group of the most respected engineers and medical officers formed an emergency council. They met daily, reviewing resource levels, assessing risks, and issuing temporary directives. But the council had no real authority beyond what the community chose to grant it. And in a closed habitat with no escape, authority is a fragile thing. The council quickly realized that survival depended on transparency. Every decision had to be explained, every resource allocation justified. If people suspected favoritism or secrecy, trust would erode and the colony would fracture. So they began holding open forums, broadcasting their meetings on the internal communication network. Any colonist could attend, ask questions, or challenge a decision. The council's role was not to rule but to coordinate. They were the ones with the most information, not the most power. Over time, the community experimented with different forms of decision-making. Direct democracy worked for some questions. Should the colony attempt a risky mining operation, a simple vote settled it. But on other issues like long-term energy rationing, a direct vote could be swayed by emotion rather than data. The colony needed a way to balance speed with deliberation. They created a hybrid system. For routine operational matters, the council had authority to act. For major changes, such as altering the distribution of water rations or deciding whether to launch a salvage mission, a 2/3 vote of the entire colony was required. Some colonies, in the stress of isolation, might drift toward more rigid structures. A strong leader might emerge, someone decisive and confident, who centralizes control. In the short term, this can be efficient, but over years it creates a dangerous dependency. If that leader makes a mistake, the entire colony suffers. And if they become unwilling to listen, dissent can turn into rebellion. The colony's emergency council recognized this risk and built in safeguards. No single person could authorize a critical life support shutdown. No decision could be made without a recorded rationale, and any colonist could call for a review of any council decision, triggering a full community discussion. Resource allocation was the most sensitive issue. When every calorie and every watt-hour is precious, the way they are distributed defines the colony's social contract. The council developed a system based on need and contribution. A colonist performing strenuous physical labor received slightly more food. A person recovering from illness received priority access to medical supplies. But the system was not rigid. If someone needed extra support for a temporary reason, the community could approve a special allocation. The key was that the rules were public, the data was shared, and exceptions were debated openly. Long-term planning required thinking beyond the immediate crisis. The colony had to decide whether to invest resources in expanding the hydroponic farm or building a new solar panel array. These were not choices that could be made by a quick vote. They required models, projections, and patience. The council formed a small planning committee that included specialists in engineering, agriculture, and biology. This committee produced detailed scenarios showing the trade-offs of each path. The community then debated the options in a series of town hall meetings. The final decision was never unanimous, but it was understood. Everyone had been heard. The governance system that emerged was not a copy of any Earth government. It was a response to the colony's unique conditions. It was pragmatic, flexible, and accountable, and it worked because every colonist knew that the alternative was chaos. The system was not perfect. There were arguments, hurt feelings, and moments of frustration. But the colony survived because its people found a way to make decisions together, even when those decisions were painful. The structure they built was not just a set of rules, it was a shared commitment to a future they were building with their own hands. And every day that the colony endured, that commitment grew stronger. A more intimate question soon pressed against the community's survival calculations. The colony had solved many problems, but it could not solve the biological reality that people age, grow frail, and eventually pass. Without Earth providing new arrivals, the population was a closed system, and every birth, every death, every aging body changed the equation. The colonists had to decide what kind of future they were building, not just for themselves, but for the generations that might follow. Reproduction became a topic that moved from the private sphere into the community conversation. On Earth, having a child was a personal choice. In a sealed habitat with finite resources, it became a collective decision. Every new person required food, water, oxygen, living space, education, and medical care over a lifetime. The colony had to ask itself, could it support another human being? And if so, how many? The first discussions were awkward and hesitant. No one wanted to dictate such a fundamental aspect of life, but the alternative was worse: unplanned births that strained resources and created resentment. The colony began to develop guidelines, not strict prohibitions, but a framework. Couples who wished to have a child would submit a request to the community council. The council would assess current resource levels, projected availability over the coming years, and the potential impact on the colony's balance. It was not about permission in a controlling sense. It was about transparency and shared responsibility. If a child arrived at a time of scarcity, everyone would feel the strain, so the community chose to plan together. Genetic diversity became a quiet concern that grew louder with each passing year. A small population, say 50 or 100 people, carries a limited pool of genes. Over generations, that pool would shrink. Close relatives would have children, and the risk of inherited health challenges would rise. The colonists understood this from basic biology. They began maintaining a genetic registry, not as a tool for selection, but as a map. They could see who carried which traits, where the overlaps were, and how to guide future pairings toward diversity. The registry was voluntary and confidential. Its purpose was to inform, not to compel. The colony might eventually need to accept that some degree of genetic narrowing was unavoidable. But they could slow it. They could encourage partnerships between individuals from different original crews or different regions of Earth. They could store genetic material from colonists who passed, preserving their contribution for future generations. The process was clinical in description but deeply human in practice. People were not just individuals, they were carriers of a lineage that might stretch into a new branch of human history. Lifespan extension offered another pathway to stability. Medical advances, even in a constrained environment, could push the boundaries of human longevity. Better nutrition, precise monitoring of health markers, reduced exposure to environmental toxins, and carefully managed radiation shielding could all add years to a colonist's life. The colony's doctors studied the data from Earth's longevity research, adapting the most practical interventions. They focused on the basics: preventing chronic disease, managing inflammation, and maintaining cardiovascular and bone health in low gravity. Simple measures like daily exercise regimens, supplemented with medication that could be locally produced, made a measurable difference. A colonist who might have lived to 70 on Earth could reach 80 or 85 in the colony. That extra decade was not just a gift to the individual, it was a gift to the community. An experienced engineer could train apprentices for longer. A skilled botanist could refine crop strains over more growing cycles. The knowledge accumulated across a longer life became a resource in itself, but lifespan extension also created tension. If people lived longer, the population would age more slowly. The elderly would remain active and contributing, but they would also consume resources for a longer period. The colony had to balance the value of experience against the reality of finite supplies. There was no easy answer, only ongoing negotiation between generations. The cultural implications of controlling fertility ran deep. On Earth, having children was often tied to identity, family legacy, and social expectation. In the colony, those norms could not simply be transplanted. The community had to build a new understanding of what it meant to be a parent, a child, a family. Some colonists chose not to have children at all, dedicating their energy to the colony's survival. Others saw parenthood as the ultimate act of hope, a declaration that the colony was not just surviving but building a future worth inheriting. The colony celebrated births with a ceremony that had no Earth equivalent. The community would gather in the largest common space, and the parents would place the infant in a small cradle woven from plant fibers grown in the hydroponic bay. Each colonist would offer a blessing, a single sentence of hope for the child's life. It was a simple ritual, but it carried immense weight. It said, "This child belongs to all of us. We will all help raise it. We will all share in its future." The decision to limit births when it came was the hardest. At certain points, the colony's resource projections might show that having a new child would push the community into deficit. The colony would need to ask some couples to wait or to forego parenthood altogether. This was not a decision taken lightly. It was discussed in open forums. The data was presented, the community voted, and those who could not have a child due to these constraints were offered other roles, other forms of contribution, other ways to feel that their lives mattered to the colony's future. The colony might also face the possibility of controlled population decline. If resources dropped below a threshold, the community might decide not to replace every person who passed. The population would shrink slowly, matching the available carrying capacity. It was a grim calculation, but an honest one. Better to have fewer people living well than many people suffering. The colony learned to think in terms of sustainability over centuries, not just the immediate year. The quiet truth was that the colony was not just managing a population. It was managing a legacy. Every decision about reproduction, lifespan, and decline was a decision about what kind of human society would survive in this new environment. The colonists were writing a new chapter of human history, one where the basic rhythms of life, birth, growth, aging, and passing, were no longer personal matters but shared responsibilities. The weight of that responsibility was immense, but so was the hope that came with it. The colony was not just a place to live, it was a seed carrying the potential for a civilization that could one day grow far beyond the walls that now held it. That seed of civilization would wither without knowledge to sustain it. A colony might have enough food and water to survive the first few years, but if the children growing up inside those walls never learn how to maintain a water recycler or calibrate an oxygen sensor, the entire enterprise collapses within a single generation. The transfer of knowledge from one set of hands to another becomes the most urgent long-term project the community undertakes. It is not enough to keep the adults alive and competent. The colony must ensure that the skills, the methods, and the deep understanding of every system are passed along to those who will take over when the original colonists grow older or pass away. Children born in the colony will inherit a world they did not design. They will breathe air processed through machines they did not build, drink water recycled through pipes they did not install, and eat food grown in systems they did not create. They will have no memory of Earth, no intuitive sense of what it means to stand under an open sky or feel rain on their skin. But they must understand how every pipe, every circuit, every valve, and every biological process works because their survival depends on it. The colony cannot afford to raise a generation that only consumes without comprehending. The classroom becomes the most vital room in the habitat, even more important than the workshop or the hydroponic bay. The colony's children learn by doing. A lesson on water chemistry happens alongside a real filter replacement. A class on plant biology takes place among the grow trays, with students measuring nutrient levels and adjusting pH under the watchful eye of an experienced botanist. Mathematics is taught through practical problems. How much power do 3 solar panels produce over a 14-day lunar night, and how many batteries are needed to store it? Physics is learned by repairing a stuck airlock door. Engineering comes alive when a 3D printer jams and a student must disassemble it, clear the blockage, and recalibrate the nozzle. The curriculum is not abstract. It is survival dressed as education. Artificial intelligence tutors fill the gaps that human teachers cannot cover. The colony's central computer contains vast digital libraries filled with textbooks, recorded lectures, interactive simulations, and step-by-step guides for nearly every task imaginable. An AI tutor can adapt to a student's pace, repeating a concept until it sticks, offering alternative explanations, and running virtual experiments that conserve real resources. The tutor never gets tired, never loses patience, and never forgets a detail. It is the closest thing the colony has to a full faculty of experts living inside its walls. But the AI is only as good as the data it holds. If the digital library was incomplete at the time of the cutoff, those gaps become permanent blind spots in the education of every child. The colony's leaders realize early on that they must prioritize the integrity of their stored knowledge. They create multiple backups of the most critical educational content, storing copies on different drives in different modules, and even printing key reference texts on paper as a last resort. A fire or a power surge that destroys one copy cannot be allowed to erase an entire field of knowledge. Specialized knowledge is the hardest to preserve. The colony might have one expert in radiation shielding who understands the nuances of local geology and the best ways to layer regolith for maximum protection. When that person passes, their knowledge could vanish unless they have trained a replacement. The colony creates a formal apprenticeship system. Every specialist takes on at least one student, sometimes more. The student shadows the expert, learns the trade, asks questions, and eventually performs tasks under supervision. The goal is not just to replicate skills, but to transfer the judgment that comes from experience. A textbook can describe the steps to calibrate a radiation detector, but only a mentor can teach the student to recognize the subtle signs of a sensor beginning to drift. The colony also encourages cross-training. An engineer might learn the basics of hydroponics, a botanist might learn to weld, a medic might learn to operate the water recycling system. This redundancy means that if one person is injured or unavailable, the colony does not lose the ability to perform a critical task. The community becomes a web of overlapping skills, each person a node in a network of competence. The risk of knowledge loss haunts every decision. The colony cannot afford to assume that a skill will survive simply because it was once documented. Documents can be lost, mislabeled, or written in a way that assumes prior understanding that no longer exists. A manual written for experienced technicians might be incomprehensible to a 16-year-old who has never seen a particular component. The colony addresses this by creating its own local knowledge base. Every time someone figures out a repair or develops a new technique, they record it in a shared database. They write it clearly, step by step, assuming the reader knows only what a colonist born in the habitat would know. The language is simple. The diagrams are drawn by hand if the computer cannot render them. The colony is building a living encyclopedia, one that grows with each success and each failure, and that will be handed down to the next generation as the most precious inheritance they can leave. Teaching itself becomes a respected vocation. The colonists who are best at explaining concepts and inspiring curiosity are given time and resources to focus on education. They are not pulling double shifts in the hydroponic bay. Their work is the classroom, and their product is a generation that can keep the colony alive. The community understands that a good teacher is worth more than a spare solar panel or an extra water tank. A teacher multiplies their value by passing it into dozens of minds that will then pass it further. The colony measures its wealth not in stored resources alone, but in the depth of understanding distributed across its population. A child who can diagnose a failing pump and repair it is an asset that will yield returns for decades. A child who can teach another child to do the same is an asset that compounds forever. The weight of this responsibility settles into the quiet moments of the colony's life. Parents watch their children solve problems that would have stumped Earth-trained engineers. They see a 12-year-old calmly recalibrate an air scrubber, their small fingers moving with precision, their eyes scanning readouts with the focus of a veteran operator. The children do not find this remarkable. It is simply the world they know. Their minds are shaped by the environment they inhabit, and that environment demands competence. The colony is raising a generation that will not mourn Earth because they have never known it, but it must also raise a generation that can carry the knowledge of Earth forward, understanding the principles that keep them alive while adapting them to the reality of their new home. The knowledge base they build and the minds they fill will determine whether the colony remains a fragile experiment or becomes the foundation of a civilization that lasts beyond any single lifetime. And that work begins with a single lesson taught one student at a time, in a room where the walls are metal and the ceiling holds recycled air, but where the future is being built with every question asked and every answer understood. Money became meaningless the day the last supply ship failed to arrive. On Earth, currency is a promise, a stored belief that a piece of paper or a digital entry can be exchanged for something real at a later time. But in the colony, that promise depended entirely on Earth honoring it. Without Earth, the entire financial system that the colonists had carried with them evaporated overnight. Bank accounts became historical records. Credit cards turned into useless plastic rectangles. The numbers that had once defined wealth, status, and purchasing power now meant nothing because there was nothing left to purchase. The shift happened fast, but it was not chaotic. The colonists understood instinctively that value had to be redefined from the ground up. The first thing to acquire worth was anything essential to survival: water, energy, food, breathable air, and the materials needed to maintain life support. A liter of clean water became more valuable than any amount of currency ever printed. A spare solar panel was worth more than a gold bar. The colony did not need a central bank. It needed an honest accounting of what was actually present in the habitat. Barter emerged as the simplest and most immediate system. A colonist with extra rations could trade them to someone who had a spare tool. An engineer who repaired a pump might receive a portion of someone's future harvest. The transactions were direct, personal, and transparent, but barter has limits. It requires a coincidence of needs. If you need a new filter but the only person who has one does not need anything you can offer, the trade stalls. The colony needed a more flexible medium. Time became the first alternative currency. The concept was simple: 1 hour of labor, regardless of the task, earned one-time credit. An hour spent repairing a water recycler was worth the same as an hour spent teaching a child to calibrate a sensor or an hour cleaning the common areas. The colony's time bank operated on trust and mutual accountability. Every colonist recorded their hours worked and could draw on those credits to request help from others. The system balanced itself over weeks and months because everyone needed something eventually. But not all labor is equal. An hour of a skilled medical officer's time during an emergency is not the same as an hour of routine maintenance. The colony quickly adjusted, creating a multiplier system. Critical skills, tasks that involved higher risk, or work that could only be performed by a few individuals earned additional credits. The medical officer received a premium for surgery. The engineer who climbed the exterior to repair a solar array earned extra for facing the danger. The adjustment was debated openly and adjusted frequently. What mattered was that the system felt fair and that it motivated people to contribute where they were most needed. Resource-based credits offered another layer of economic structure. The colony began to issue credits backed by physical resources. A colonist who discovered a new deposit of water ice or who processed a batch of regolith into usable metal received resource credits that could be redeemed later for a share of the colony's common stockpile. This tied value directly to tangible goods, avoiding the abstract nature of pure time credits. A resource credit was a claim on something real, like a specified amount of water, a ration of electricity, or a quantity of recycled plastic. Over time, the colony's economy became a hybrid system. Time credits covered everyday services and routine labor. Resource credits covered larger transactions involving physical materials. And direct barter handled the small, personal exchanges that kept the community connected. A colonist might trade a freshly grown tomato for a spare battery. Another might offer 2 hours of tutoring in exchange for help repairing their quarters. The economy was not efficient in the way Earth's global markets were efficient. It was slower, more localized, and deeply personal. But it was also resilient because it was built on relationships rather than abstract algorithms. Water became the benchmark of value, the unit against which everything else was measured. A colonist could earn a water credit by performing a task for the community, and that credit could be exchanged for a supplementary ration beyond the baseline allocation. Water was not just drinking supply, it was coolant, radiation shielding, and the medium for hydroponic growth. Its value touched every system. A colonist who accumulated excess water credits could trade them for extra energy allowance or priority access to the workshop's 3D printer. The colony published a periodic value index, a simple chart showing how many water credits a kilowatt-hour of energy was worth, or how many credits a kilogram of recycled metal yielded. The index was not set by a central authority. It emerged from the trades people actually made. If someone offered to trade 10 water credits for a repair job and someone accepted, that set a precedent. Over time, these precedents accumulated into a shared understanding of relative worth. The economy was not planned. It grew like a garden from the choices of individuals trying to meet their needs. The shift away from Earth's money model changed how people thought about work and contribution. On Earth, a person might work for wages that had no direct link to the actual value of their labor. In the colony, every task had a visible, measurable outcome. Fixing a pump meant more water available for everyone. Growing a successful crop meant more food on the table. Teaching a skill meant a more competent community. The connection between effort and result was immediate and clear. People began to take pride in their contributions in a way that felt different from earning a paycheck. They were not accumulating abstract wealth. They were building the conditions for their own survival and the survival of everyone they knew. The old economic labels faded. There were no rich or poor colonists in the traditional sense. There were people with many skills and people with fewer, but everyone had a baseline of support because everyone was needed. A colonist who could not perform heavy labor might still contribute by teaching, documenting, or caring for children. The colony could not afford to discard anyone. The economy was designed to include, not exclude. This does not mean there was no inequality. Some colonists accumulated more time credits or resource credits than others, and they could use those credits to secure better quarters, more privacy, or access to luxury items like a personal music player or a rare book. But the inequality was bounded. No one could hoard so much that others went without essentials because the baseline allocations were fixed. The colony operated on a floor of guaranteed survival for everyone, with a ceiling determined by contribution. The economy became a tool for cooperation, not for competition. It aligned individual effort with collective well-being. The colonists learned that the true wealth of their community was not measured in credits or resources. It was measured in the ability to solve problems together. A colony where people shared knowledge, traded labor, and trusted one another was rich. A colony where people hoarded and withheld was poor, no matter how many water credits were in its reserves. The economic system they built was not perfect. There were disagreements about fairness, debates about the value of different tasks, and occasional resentment when someone felt undercompensated. But the system was alive, constantly adjusted in open forums, and always answerable to the one true measure: the colony's continued existence. And as the years passed, the memory of Earth's markets faded, replaced by a simpler understanding. Value was not a number on a screen. Value was the pump that kept water flowing, the panel that caught sunlight, the hands that repaired a leak, and the mind that taught a child to do the same. The colony had not just replaced its economy, it had rediscovered what an economy was actually for. Self-sufficiency inside a single habitat is a trap disguised as safety. A colony that grows comfortable within its own walls, that learns to recycle every drop and stretch every watt, can easily convince itself that staying put is the smartest choice. But a single location is a single point of failure. A meteorite strike, a solar flare that overloads the shielding, a slow depletion of the local ice deposit. Any of these could turn a thriving settlement into a dying one overnight. The only way to truly reduce risk is to spread it across multiple sites, to build a network of outposts that can support one another when any single node faces disaster. The colony must become a multi-world enterprise, not out of ambition, but out of the cold logic of survival. The first and most obvious target is the asteroid belt. Those drifting mountains of metal and ice are not just scenery. They are the richest accessible source of raw materials in the solar system. A single metallic asteroid can contain more platinum group metals than have ever been mined on Earth. But more importantly, they contain water, carbon, and nitrogen, the building blocks of life and fuel. A colony that learns to capture and process an asteroid gains access to resources that dwarf everything within its original habitat. The challenge is not just reaching the asteroid, but mining it, refining its materials, and transporting them back. This requires new ships, new tools, and new techniques. It also requires a fleet of small, automated miners that can operate for months or years without human intervention. Building that fleet consumes resources the colony can barely spare, but the payoff is transformative. Every kilogram of metal extracted from an asteroid is a kilogram that does not have to be recycled from the colony's aging stocks. Every liter of water mined from a carbonaceous chondrite is a liter that can support a new module or a new crew member. The colony must invest heavily in the infrastructure of extraction, knowing that the return will not come for years. The investment is a bet on the future, and the colony's leadership must convince the community that the risk is worth the reward. Other moons in the same system offer additional diversification. A colony on Mars might look to Phobos or Deimos, the two small moons that orbit the red planet. These bodies are not rich in resources themselves, but they are perfectly positioned as staging points. A fuel depot on Phobos could dramatically reduce the cost of launching missions to the asteroid belt or the outer planets. A small outpost on Deimos could serve as a communications relay and a forward observation post. Building these outposts is not about finding new resources directly, but about creating logistical hubs that make all other expansion easier. The colony must think in terms of infrastructure networks, not just isolated settlements. Mercury, the closest planet to the Sun, presents a more extreme opportunity. Its surface is baked by unfiltered sunlight, with temperatures that melt lead during the day and plunge to cryogenic cold at night. But in the permanently shadowed craters at its poles, water ice survives. And the solar energy available on Mercury is immense. A colony that builds an outpost there could generate power on a scale that dwarfs any other location in the inner system. The challenge is survival. The outpost must be shielded from radiation, insulated against extreme temperature swings, and designed to operate with minimal human presence. It would likely begin as a robotic station with automated mining and power generation, sending energy back to the main colony via laser or microwave transmission. The idea of beaming power across space sounds like science fiction, but the physics is sound. The main colony would receive a steady stream of clean energy, enough to run its factories, its farms, and its life support systems without depending on its own finite nuclear fuel. Expansion of this kind requires a level of coordination that the colony has never attempted before. Every new outpost demands resources from the main habitat. Every ship built for transport consumes materials and labor that could have been used for local repairs. Every crew member assigned to a distant station is a person not available for work in the home colony. The colony must create a planning body that can evaluate these trade-offs with clear eyes. It must model the long-term benefits against the short-term costs. And it must build a consensus among the colonists that these investments are essential for survival, not optional luxuries. The community may resist. Some will argue that every resource should be hoarded for the main habitat, that expansion is a gamble they cannot afford. The leaders must make the case that staying still is the greater gamble. A single habitat is a single basket for all the colony's eggs. The first asteroid that cracks the hull, the first solar storm that overwhelms the shielding, the first unexpected depletion of a local resource, any of these could end the entire experiment. But a network of outposts scattered across different worlds, with different environments and different resource bases, can absorb a disaster at any one node. The colony becomes resilient not by being strong in one place, but by being present in many. The vision of a multi-world civilization begins to take shape. Not as a distant dream, but as a practical survival strategy. The colony that expands is a colony that hedges its bets. It is a colony that understands that survival is not about holding onto what you have, but about reaching for what you need before you need it. And that reaching is the first step toward something far larger than any single habitat could ever contain. That leap outward demanded a leap inward in how the colony thought. The pressure of losing Earth support did not just create a shortage. It created a forcing function, a relentless push to innovate or fade. Every system that had once been designed for efficiency under ideal conditions now had to be reimagined for survival under constraint. The colony became a laboratory where the only acceptable outcome was a working solution, and the only deadline was the next failure. Closed-loop life support became the highest priority. The original system recycled water and air, but it relied on disposable filters and chemical scrubbers that would eventually run out. The colony needed a system that could regenerate itself indefinitely. The answer came from biology. Engineers and botanists worked together to design biological air filters. They cultivated specific strains of algae and bacteria in transparent tanks that were plumbed directly into the ventilation system. As air circulated through the tanks, the microbes consumed carbon dioxide and volatile organic compounds, releasing clean oxygen. The algae multiplied under LED lights, providing both filtration and a steady source of protein. The system was not as fast as a mechanical scrubber, but it was self-sustaining. It grew its own replacement parts. Over time, the colony installed arrays of these biofilters in every module, transforming the habitat into a living system that breathed with them. Energy efficiency demanded a radical rethink of every device. The colony's engineers went through every system, from the largest pump to the smallest sensor, and asked whether it could run on less power without compromising its function. They rewired lighting circuits to use motion sensors that dimmed lights in empty corridors. They replaced resistive heaters with heat pumps that moved warmth from one zone to another. They recovered waste heat from the nuclear reactor and the 3D printers, channeling it into the hydroponic bays where crops grew faster at slightly warmer temperatures. The gains were incremental, a few percent here and there, but over months those increments added up to days of extra power for critical systems. Advanced recycling went beyond water and air. The colony began treating every output as an input. Human waste was processed not just for water recovery but for nutrients and even trace minerals. Urine was distilled and the solids were dried into a powder that could be mixed into the algae feedstock. Metal shavings from the workshop were sorted by alloy and remelted into new bars. Plastic waste was shredded, melted, and extruded into new filament for the 3D printers. The colony even experimented with plasma gasification, using extreme heat to break down organic waste into its elemental components, which could then be recombined into useful compounds. The technology was energy-intensive, but the colony found that by running the process only when solar power was abundant, they could turn garbage into a treasure of hydrogen, carbon monoxide, and simple hydrocarbons. Waste valorization became a cultural shift. Nothing was thrown away because nothing was worthless. A broken tool was not garbage. It was a source of steel, copper, and plastic. A failed experiment was not a loss. It was a library of chemical samples that might be useful elsewhere. The colony developed a catalog of waste streams, each with a known composition and a set of possible uses. A container of spent algae paste could be fermented into ethanol. The ash from burned plant matter was rich in potassium and phosphorus for hydroponic nutrients. Even the dust from the air filters was analyzed for rare elements that had accumulated over time. The colony learned to see the world not as a collection of objects with fixed purposes, but as a flow of materials that could be endlessly transformed. New materials emerged from the pressure to use local resources. The colony could not rely on Earth's advanced composites or specialty alloys. It had to invent its own. Researchers experimented with mixing regolith dust with a biodegradable polymer extracted from algae. The result was a strong, lightweight composite that could be molded into panels and structural supports. They discovered that by adding a small amount of carbon fiber reclaimed from old equipment, the composite became nearly as strong as aluminum. For self-healing structures, they embedded tiny capsules of a liquid resin into the walls of critical components. When a crack formed, the capsules broke open and the resin flowed into the gap, hardening to seal the damage. The first tests were on small pipes and brackets, but the principle worked. A habitat wall that could repair its own hairline fractures was a wall that would not fail catastrophically. The pace of innovation was relentless. The colony could not afford to wait years for a research paper to be peer-reviewed. They had to try, fail, learn, and adapt in weeks. Every failure was documented not as a mistake but as data. A biofilter that clogged too quickly led to a redesign of the flow path. A self-healing capsule that hardened too slowly led to a new resin formula. The colony's workshops and labs were never silent. They hummed with the rhythm of people who knew that the next breakthrough might be the difference between thriving and barely surviving. And in that pressure, they discovered something unexpected. The innovations they created were not just stopgap fixes. They were genuinely better than the Earth-based technologies they replaced. A biological air filter that consumed carbon dioxide and produced protein was more than a replacement for a chemical scrubber. It was a more elegant solution, one that integrated multiple functions into a single living system. A self-healing composite made from local dust and algae was not just a substitute for imported steel. It was a material that could be produced anywhere with no supply chain at all. The colony had not just survived the loss of Earth's support, it had been forced to reinvent the very idea of technology, and in doing so, had created a new branch of engineering that might one day outshine everything that came before. The innovations born inside one colony did not stay inside its walls forever. Across the solar system, other settlements were also fighting the same fight, adapting, failing, and succeeding in their own ways. And sooner or later, those separate struggles had to meet. The first contact between two independent colonies would not be a handshake or a diplomatic ceremony. It would be a signal, a faint radio pulse picked up by an antenna that had been listening only to silence for years. The moment that signal is confirmed as deliberate, as coming from another human settlement, the entire calculus of survival changes. Suddenly, no colony is alone in the universe. There are others out there, each with its own stockpiles, its own knowledge, its own problems. And those others represent either the greatest opportunity or the greatest threat the colony has ever faced. Trade would be the first instinct, and for good reason. One colony might sit atop a rich deposit of water ice while another has an abundance of metallic ore. A third might have developed a particularly efficient strain of algae that yields twice the protein per watt of light. Each colony holds something the others need, and exchanging those resources could lift everyone above the subsistence line. A single shipment of rare earth elements from an asteroid miner could allow a Martian habitat to build new solar panels. A delivery of high-quality regolith binders from a lunar outpost could let a distant settlement expand its hydroponic farm. The logic is compelling. Specialization reduces waste, and trade creates abundance from scarcity. But trade across interplanetary distances is slow and expensive. A cargo pod launched from the asteroid belt might take months to reach Mars, and the fuel required to change its trajectory is itself a precious resource. The colonies would have to build a network of reliable transport, a kind of interplanetary shipping lane that operates on schedules measured in years rather than days. They would need standardized containers, agreed-upon units of exchange, and a shared system for verifying the quality of goods sent across millions of kilometers. Trust would be the most fragile link in the chain. A colony that sends a shipment of promised water must be certain it will receive the agreed-upon metal in return, not empty promises or degraded materials. The first few trades would be small, cautious, and heavily verified. Every success would build confidence, and every failure would set back the entire network. Sharing knowledge might prove even more valuable than sharing goods. A colony that has perfected a method for extracting oxygen from perchlorate-rich soil could transmit those instructions to another settlement struggling with the same problem. A breakthrough in biological filtration could spread across the solar system in hours if the communication channels are maintained. The colonies would begin to see themselves as nodes in a distributed brain, each one contributing its unique expertise to the collective intelligence. A shared repository of solutions, a library of local adaptations, would accelerate progress everywhere, but sharing knowledge also means revealing vulnerabilities. A colony that discloses its precise resource inventory might become a target for exploitation. A colony that admits to a failing life support system might be seen as weak. The calculus of trust extends to information as well. Alliances would form around shared interests. Colonies on the same planet or moon might cooperate to build joint infrastructure, a shared space elevator or a common power grid. Colonies that depend on the same asteroid belt for minerals might agree to partition the resource to avoid competition. Alliances would be formalized through agreements, treaties, or simple handshake deals, but the enforcement mechanism is always the same: mutual need. A colony that breaks a promise risks losing access to critical supplies. In an environment where survival depends on cooperation, betrayal is a luxury no one can afford. Competition would also emerge, but not necessarily in the form of conflict. Two colonies might vie for the same water-ice deposit, racing to establish a mining outpost first. One colony might develop a more efficient rocket engine and use it to dominate the transport routes. Another might hoard a monopoly on a rare technology, using it as leverage to demand favorable trade terms. The competition would be economic, not military, at least at first, but the line between economic pressure and coercion is thin. A colony that controls the only source of a vital medicine could set its price arbitrarily. Another that dominates the communication relay network could censor information. The colonies would need a set of shared rules, a kind of interplanetary compact, to prevent these pressures from escalating into something worse. The most profound shift would be cultural. Each colony, after years of isolation, would have developed its own identity, its own customs, its own way of speaking and thinking. A community that originated from a research mission on Mars might value scientific rigor above all else. A mining outpost in the asteroid belt might prize practical skill and toughness. A settlement on the Moon, built by a consortium of nations, might be more cosmopolitan and diplomatic. When these cultures meet, they would not always understand each other. Misunderstandings would arise over resource allocation, work ethic, or even humor. But over time, they would learn to negotiate not just goods but meaning. A shared vocabulary of survival would emerge, a language that incorporates the struggles and triumphs of all the colonies. The potential for a new interplanetary civilization rests on this web of relationships. Not a single government ruling from one center, but a decentralized network of interdependent settlements, each sovereign but each connected. A colony that faces a catastrophic failure would not be left to die alone, because its neighbors would have an interest in its survival. A colony that develops a breakthrough would share it, because sharing accelerates the progress of the entire network. The system would be held together not by force, but by the recognition that isolation is a slower death than dependence. The colonies would learn that the first law of survival is not self-sufficiency, but mutual reliance. And in that realization, they would begin to build something that no single planet could ever create. A civilization that spans worlds, held together by the fragile, vital threads of trade, knowledge, and trust. The solar system would no longer be a collection of lonely outposts. It would become a neighborhood. Survival was only the first chapter. The second chapter would be about building a world worth living in. Once the colony had secured its basic needs, once the hydroponic bays were producing reliably and the water recyclers were running in a stable loop, a new question began to surface, quietly at first, then with increasing urgency. What were they surviving for? The answer could not be merely avoiding death. That was a treadmill that would eventually wear them down. The answer had to be something worth reaching toward, a horizon that gave meaning to the daily struggle of maintenance and repair. That horizon was a planet transformed. Terraforming is the grandest ambition any colony could hold. The word itself sounds like something from mythology, but its meaning is simple and profound. To take an entire world and reshape its atmosphere, its temperature, its water cycle, and its soil until it can support human life without the need for pressure suits and sealed habitats. It is not a project for a single generation. It is a project for centuries, for a civilization that thinks in terms of geological time rather than election cycles or quarterly reports. But the colony had the one thing that Earth had never fully committed: time and necessity combined. They could not leave. They had to make this world their home, or their descendants would never know any other. The first step toward terraforming a world like Mars is to thicken its atmosphere. The existing air is thin, less than 1% of Earth's pressure, and it offers almost no protection from solar radiation. But frozen carbon dioxide in the polar caps and trapped in the soil represents a vast reservoir of gas. If the colony could release that carbon dioxide into the atmosphere, the pressure would rise gradually. A thicker atmosphere traps more heat, which in turn releases more carbon dioxide, creating a self-reinforcing cycle. The colony would need to devise ways to melt the polar caps, perhaps by spreading dark dust on the ice to absorb more sunlight, or by constructing orbital mirrors that focus solar energy onto the frozen regions. It would be slow work measured in decades, but each small increase in atmospheric pressure would bring the planet one step closer to a state where liquid water could exist on the surface. Orbital mirrors are not a fantasy. They are a practical engineering challenge, one that the colony could begin to address once it had established a modest industrial base in space. A mirror as wide as a city block, made from thin reflective material mined from asteroids, could be placed in a stable orbit and angled to reflect additional sunlight down to the surface. A constellation of such mirrors could raise the average temperature of a planet by several degrees over a few decades. The mirrors would need to be assembled in orbit, maintained against micrometeorite damage, and adjusted as the planet's climate responded. The colony would learn to think of space not just as a void to cross, but as a resource to be shaped, a volume where light itself could be directed like a tool. The release of greenhouse gases would need to be accompanied by a steady infusion of oxygen into the atmosphere. The colony already knew how to extract oxygen from regolith using molten salt electrolysis. Scaling that process up to planetary levels would require vast arrays of automated processing plants scattered across the surface. These plants would pull oxygen atoms from the iron oxide minerals that give Martian soil its rusty color, releasing the gas into the atmosphere and leaving behind metallic iron as a valuable byproduct. Over centuries, the oxygen concentration would rise to levels that could support respiration without a pressure suit, at least at lower elevations where the atmospheric pressure was highest. It would not be Earth's air, but it would be breathable, and that would be a transformation unlike anything humanity had ever achieved. Large-scale habitat expansion would begin long before the terraforming was complete. The colony could not wait for the air to turn sweet. It needed more living space, more industrial capacity, more redundancy against failure. The solution was to build underground, using the planet's own crust as shielding against radiation and temperature extremes. The colony would excavate vast caverns, carving out chambers that could hold entire neighborhoods, farms, and factories. The excavated rock would be processed into building materials, and the caverns would be pressurized and lit with artificial sunlight. A single underground city could house thousands of people, protected from the surface's harsh environment while the slow work of terraforming continued overhead. These underground cities would be connected by tunnels, forming a network of habitable space that spiderwebbed beneath the planet's surface. The colony would no longer be a single habitat. It would be a civilization of interconnected vaults, each one a self-contained world. The quest for full self-sufficiency extended beyond the planet itself. The colony had to achieve what engineers call closure, a state where no external inputs are needed for centuries. Every atom of carbon, every molecule of nitrogen, every trace element essential for life and industry had to be cycled indefinitely. The colony had to become a closed loop at planetary scale. This meant recycling not just water and air, but every nutrient, every metal, every plastic. It meant designing systems that could break down waste products into their constituent elements and rebuild them into anything the colony needed. It meant that nothing, not a wisp of exhaust, not a fleck of dust, not a drop of condensate, would be allowed to leave the system without being captured and reused. The technology for this level of closure did not exist when the colony left Earth. They would have to invent it, test it, and refine it over generations. The aspirational nature of these goals changed how the colony thought about itself. Survival was no longer the only measure. There was now a vision, a long arc of progress that stretched beyond any single lifetime. A colonist might not live to see the first breathable air outside the habitat, but they could work toward that day, knowing that their labor would be inherited by their children and their children's children. The colony began to plan in terms of centuries. They created a timeline, not a rigid schedule, but a map of milestones, thickened the atmosphere by 1% within 50 years, launched the first orbital mirror within a century, establish the first underground city within 2 centuries, begin oxygen production at industrial scale within 3 centuries. Reach the point where a human can walk on the surface without a suit within 1,000 years. The timeline was not the point. The point was that the colony had a purpose beyond the next meal or the next repair. They were no longer castaways surviving on luck and ingenuity. They were the founding generation of a new branch of human civilization, one that would eventually transform a dead world into a living one. The crisis that had severed them from Earth had also freed them from Earth's limitations. They could think on a scale that no Earth-bound society had ever dared. They could build not just for themselves, but for a future that would unfold over millennia. The colony looked out at the barren, dusty landscape beyond their windows, and instead of seeing a prison, they saw a project. The red horizon was no longer a boundary. It was a blank page, waiting for the first stroke of a story that would take 1,000 years to write. The umbilical cord that once connected every colonist to Earth was not just made of metal and radio waves. It was made of memory, of identity, of 1,000 small assumptions about who they were and where they belonged. When that cord was severed, the colonists did not lose only supplies and support. They lost the mirror in which they had always seen themselves reflected. For years, every aspect of their lives had been measured against a distant home planet. Their food was judged by Earth standards, their architecture mimicked Earth designs, their celebrations followed Earth calendars. They were, in every meaningful way, a branch still attached to a tree they could no longer reach. But the branch had to learn to grow its own roots. That transformation began not in a laboratory or a planning meeting, but in quiet moments of realization. A colonist born in the habitat might ask what a forest really feels like, not the holographic simulations they had seen, but the actual sensation of bark under their fingers and wind moving through leaves above their head. The adults would try to describe it, but the words fell short. The child would accept the description politely, but their understanding of the word forest would forever be tied to the hydroponic bay, to the smell of nutrient solution and the hum of grow lights. That child was not an earthling. They were something new. The emotional relationship with Earth became complex and layered. Some colonists clung to their memories with fierce devotion, decorating their quarters with images of oceans and mountains, celebrating holidays according to the old calendar, and telling stories of a world that no longer existed as a tangible place but as a mythic origin. These colonists became the keepers of heritage, the ones who ensured that Earth was not forgotten. They taught the children the names of extinct animals, the words to old songs, the recipes for dishes that could never be made again because the ingredients no longer existed. Their devotion was a form of love, but also a form of grief. Others took a different path. They saw Earth not as a lost home, but as a chapter that had closed. Their identity was no longer bound to a planet they could never return to. They began to embrace the colony as their true home, not a temporary shelter but a permanent world. They modified the habitat to suit their needs rather than mimicking earthly designs. They reorganized the daily schedule to match the local day length instead of the familiar 24-hour cycle. They created holidays that celebrated local events, the first harvest from a new hydroponic bay, the anniversary of the colony's founding, the day they successfully extracted water from a new ice deposit. These new traditions carried no nostalgia. They were born from the ground beneath their feet. The tension between preservation and transformation was not a conflict to be resolved. It was a creative force that shaped the colony's culture. Both perspectives were necessary. The preservationists ensured that the knowledge of Earth survived, not as a museum piece but as a living reference library. Future generations could study Earth's art, its science, its philosophy, and its mistakes. They could learn from the long history of a planet that had nurtured humanity for hundreds of thousands of years. That heritage was not a burden to be shed. It was a treasure to be understood. But the transformationists ensured that the colony did not become a static imitation of a lost world. They pushed for innovation, for adaptation, for a culture that reflected the unique conditions of their environment. The colony's music began to incorporate the sounds of its machines, the rhythmic hum of air circulators, and the low thrum of water pumps. Its art depicted the stark beauty of the local landscape, the deep shadows of craters and the pale light of distant stars. Its stories focused on survival, on ingenuity, on the bonds formed in the crucible of isolation. A new mythology began to take shape, one where the old heroes of Earth were joined by local legends. The colonist who first repaired the failing oxygen scrubber became a figure of quiet reverence. The engineer who designed the first self-healing wall panel entered the oral tradition. These were not mythical figures in the ancient sense. They were real people whose actions had saved lives, and their stories were told and retold, gaining depth and meaning with each telling. The colony's identity was not a rejection of Earth. It was an expansion of what it meant to be human. The species had spread beyond its cradle, and with that spread came a natural divergence. The children born in the colony would have bodies adapted to lower gravity, immune systems shaped by the local microbiome, and minds that perceived space and time differently because their world was smaller and more intimate. They would never feel the ache of missing Earth because they had never known it. Their home was the colony, and that was enough. The older generation had to learn to let go of the idea that Earth was the only real world and that everything else was a pale imitation. They had to accept that their children's identity was valid, complete, and beautiful in its own right. The colony began to hold formal events that acknowledged this dual heritage. One day each year was set aside as Earth Day, not the environmental celebration of old, but a day to remember the planet of origin. Colonists would share stories, display images, and teach the children about the blue world that had once been humanity's only home. Another day was Foundation Day, celebrating the colony's own birth and the struggles that had shaped it. On Foundation Day, the focus was entirely local. They would honor the original crew, retell the stories of the first difficult years, and reaffirm their commitment to building a future in this place. The 2 days were not in competition. They were two sides of a single identity. The colonists were the inheritors of Earth's legacy, but they were also the architects of something new. Their culture was a bridge stretching from a past they could not return to, toward a future they could not fully imagine. And on that bridge, they walked together, carrying the best of what had been, while building what had never been before. The question was no longer how to survive. It was what kind of civilization they would choose to become. The answer to that question is still being written, but the shape of it is already clear. The path from crisis to resilience runs through every system we have explored. The moment Earth fell silent, the colony faced a choice that no training manual had prepared them for. They could have fallen into chaos, letting fear and competition tear apart the fragile bonds that held them together. Or they could turn inward and discover resources they never knew they had, not in cargo bays or storage lockers, but in the minds and hands of every person present. The colonies that survived did not do so because they were luckier or better equipped. They survived because they chose to adapt, to share, to learn, and to build something new from the ruins of the old order. The arc from helpless dependency to innovative self-sufficiency is not automatic. It is earned through thousands of small decisions made under pressure. The colony learned to extract water from ice, grow food in recycled air, generate power from local sunlight, and fabricate parts from the dust beneath their feet. They learned to govern without a constitution, to trade without money, to teach without a curriculum, and to find meaning without a home planet to return to. Every failure taught them a lesson that no textbook could provide. Every success built confidence that the next challenge could be met. The central truth that emerges from this story is both humbling and inspiring. Space colonies, when forced to rely entirely on themselves, will either collapse into disorder or transform into remarkably inventive, self-reliant societies. There is no middle ground. The margin for error is too thin, the consequences of mistakes too severe, but the potential for growth is equally immense. A society that learns to close its loops, to value every resource and every person, to think in centuries rather than years, is a society that can endure far longer than any Earth-based civilization has ever managed. This is not a story about technology alone. It is about human nature under the most extreme conditions imaginable. It asks us to reflect on our own world, on the dependencies we take for granted, on the systems we assume will always be there. The colonies that thrived did so because they prepared not just with hardware but with foresight, with redundancy, with a culture of collaboration. They understood that the worst time to plan for a crisis is when the crisis has already arrived. So here is the call, not to build a spaceship or stockpile supplies, but to think deeply about what it means to be ready. The future of humanity in space will be shaped by the choices we make long before the last ship leaves Earth. Will we design our colonies to be resilient from the start, or will we leave them to discover resilience the hard way? The answer to that question may determine not just whether we survive beyond our home planet, but what kind of species we become when we do. The story of these colonies is still unfolding, and we are the ones who will write the next chapter.